These are video help solutions to discuss the solutions for this laboratory that we would have done actually some measurements associated with this, but you have to use your imagination here. So we've got a meter stick going out over here. Of course, it wants to if it's pivoted at its left end, it wants to fall under the influence of gravity, but we're holding it up with a force sensor that maybe we hold in our hand or we attach to one of those lab stands, and a string going down attached to a certain point. And where that force sensor is attached via the string, we can change that. So we can attach it at the 90, 70, 10 centimeter marks, and so on. So in this first case, we attach it at the 90 centimeter mark, and the first thing we're supposed to do is draw all three forces acting on the stick when it's balanced this way. Okay, so the force sensor is of course going to be pulling up at the 90 centimeter mark. So that's this force right here. This is actually supposed to be horizontal, but my scan got a little bit wonky here. So this is supposed to be going directly vertical, and the stick is supposed to be the same as this picture up here. That's the best I could do. And the weight force, we're told at the top we're supposed to pretend it's acting at the center of mass, so we know the weight of this, so it's got a certain weight force going down. And then there's also an upward force from the pivot. In other words, if the pivot weren't exerting a force, these two things, we got a sort of a smaller force here and a bigger force there, this would start rotating down, so the pivot's got to push up too. We can figure out what those forces have to be, and then we'll know how long to draw the arrows and actually what their directions are going to be. Well, we know the weight force is down, so we know its direction, and we know the string force is up. So conditions for equilibrium are the sum of the torques equals 0 and the sum of the forces equal to 0. We're going to start with the sum of the torques equal to 0 with respect to this axis. And there are only two non-zero torques. This force from the pivot doesn't exert any torque on the rod about this axis because its moment arm is 0. So if we call counterclockwise the positive direction, the string force is a positive torque and the weight force is a negative torque. And I add those together and we can figure out what the required string force is, assuming that it's in equilibrium. So that gives us 0.644 newtons. Similarly, if we then say the second condition on equilibrium is that the sum of the y components of these forces also has to be equal to 0. I took plus y to be up. It's a little bit blurred over there, but there's a plus y axis going up. So these two forces, well, let's see. We know this one's up and this one's down, and we can assume this one is going up. If we get a minus sign, then we'll know we're wrong. So let's assume this one is going up. So we would have F pivot, y component, minus the weight force plus the string y component force, which we now know. Set that equal to 0 and solve for the pivot force. And we know what the weight force is. We can calculate that in there. So plug that in, we can get the pivot force. And we find out the pivot force is positive, so our guess was correct that it was upward there. The pivot is actually pushing up at the pivot location. Moreover, we can see the relative sizes of these. The weight force is the biggest, a little bit bigger than 1 Newton in magnitude, and then the pivot force is about half that size, so that means relative to the weight force, this should be about half the length, and then the string force is just a tiny bit bigger than the pivot force. I couldn't really tell the difference here, so they're almost the same. This is supposed to be just a little bit longer than the pivot force, so that tells us the directions. And we can also calculate the torques by multiplying those forces times their moment arms. Again, the pivot force torque about this point is 0 because that force has 0 moment arm. So I've labeled those in there. Okay, and then the other parts are really repeats of that. So we're just going to do the same calculations we did up here, but the only change in the second part is that the 90 centimeters changes to a 60 centimeters. So this becomes a 0.6. And I guess this becomes a 0.6. And we rerun all the calculations and we find things change. Of course, the weight force doesn't change. The weight force is what it is. But the string force that we need actually gets bigger. It was, what was it, 0.6 up in this case? Now it's 0.8 0.99, so about 1 Newton of force. So it's quite a bit bigger than it was before. So this one's getting longer. It's a little bit less still than the weight force in magnitude. So this should be the longest one. This one's just ever so slightly shorter. And now the pivot force, after we run the numbers through, is 0.199 newtons. So it's significantly smaller than these, about 1/5 the length of these two. And we calculate the torques the same way. Interestingly enough, in the third case, when we run those numbers through, we change the 0.9 now to 0.2. So we're pulling up with the string right here. And something interesting happens. When we run the numbers through, we now find that the pivot y component ends up being negative. So we guessed upward. We found that pivot force y component is negative, and that means it's actually going downward. And so the pivot isn't holding up the left end, it's pulling down on the left end in this case. But running the numbers through, now the string force is the largest force. It's almost 3 newtons. The weight force, of course, is what it was before. It's the same in all three of these cases, a little bit bigger than 1. And the pivot force is now the second biggest one. So this is the longest, this is the next longest, and this one is the same as it was before. And the torques are calculated the same way. Last question is, at which centimeter mark would you attach the string so that the pivot exerts no force on the stick? In other words, when we attach the string way over here, the pivot force pushed up, and then it started getting smaller, and then it ended up pulling down when we moved the string force far enough in. At some point, it looks like it would cross, it would go from positive to negative. Where is that? Well, if you think about it for a second, you can see that if I pull up with the string force at the 50 centimeter mark, then the torque due to the string foot, if I pull up there with the right amount, then there's no required pivot force at all. In other words, the ruler or the meter stick would stay in static equilibrium even if there were no pivot over at this end, because we could just sort of balance it by a string in the middle. And then, the two vertical forces of the weight force and the string force would exactly cancel, and the two torques about here would exactly cancel, and it would be in equilibrium. So it's at the 50 centimeter mark. I mean, you could check that if you wanted, but you can kind of see it or just use your intuition to see that. So that's the solution to our lab exercise.